Hi guys, welcome to your last bit of content of pre-calc for the year. So this video is just really going to explain the concept behind nth roots of complex numbers. I'm not sure if we'll get to too many examples, but don't worry, I'll be posting example videos as well. So we're going to be talking about nth roots of a complex number, okay? Basically, we're reversing what we did yesterday, which was de Moivre's theorem, okay? So we're going to say a complex number, v is equal to a plus bi, is the nth root of z if when we raise that complex number v to the nth power, we get z. And if z is equal to 1, then v is the nth root of unity, okay? So that is a lot all packed into there. Okay, I promise we're going to break this down a little bit. So first thing we're going to do is we're going to find the cube roots of 1. All right, so remember cube roots are something that you would multiply 3 times by itself to get to a number. So the cube roots of 1, well, the obvious one is 1 because 1 times 1 times 1 is equal to 1. Okay, you guys all passed into high school math, so hopefully you know that. I'm going to go out on a limb here, though, and I'm going to say that the cube root of 1 is also equal to negative 1/2 plus square root of 3 over 2i. Now, I'm also going to go out on a limb here and say that the cube root of 1 is equal to negative 1/2 minus the square root of 3 over 2i. So what I'm saying here is that if I multiply negative 1/2 plus square root of 3 over 2i times itself 3 times, that's equal to 1. Same thing with the one below that. If I multiply negative 1/2 minus square root of 3 over 2i 3 times, that's also equal to 1. If you want to pause the video, check that, go for it. Remember that I squared is equal to negative 1. That's going to help you out a lot. How in the world did I get that? Okay, so basically what we're doing here is we have this big box that gives us a formula. So to get to that formula, I'm kind of going to break down reversing de Moivre's theorem for you, all right? So we're going to say that we have a complex number v, all right? And v is equal to k, which k is your radius in this case, times the cosine of alpha. That's your angle alpha. I used to call that fish when I was in college. We'd say cosine of fish. My professors didn't really like that, but oh well, if you want to call it fish, that's fine. Cosine of alpha plus I times the sine of alpha. So in this case, k is your radius, alpha is your angle. Okay? And then we're also saying that if we raise v to the nth power, we get z. All right? And z is defined up here. Z is equal to r times cosine theta plus I sine of theta. So, using de Moivre's theorem from yesterday, I hope you remember back that far, de Moivre's theorem, v to the n is equal to k to the n times cosine of n alpha, put that in parentheses, plus I sine of n alpha. And remember that this is also equal to z. So since v to the n is equal to z, and z is equal to r times cosine theta plus I sine of theta. All right, take a minute, make sure that you're there. This is z. That was a really ugly z. Oh, hello. And this is v to the n. All right? So, since these two expressions are equal, we can equate some things together, all right? So, we know that since these are equal, k to the n has to be equal to r. So, in your complex number v, your radius to the nth power has to be equal to your radius of z. So, we can write r is equal to k to the n. Now, if we want to find out what k is equal to, we can take the nth root of both sides. So r, taking the nth root of that, is equal to k. All right? That's your first component of this whole thing. Now also, since we have the cosine of n alpha and the sine of n alpha, we can say that those are equal to theta. So we can say n alpha is equal to theta. But remember, n alpha can be equal to any coterminal angle of theta. So if n alpha is equal to, I don't know, pi over 4, it's also equal to 9 pi over 4. And what would the next one be? I can't think off the top of my head. Wow, that's kind of embarrassing. Whatever. So we have to add 2 pi times some integer k. All right, these two k's are not the same thing. All right, this is just saying how many times we're going around the unit circle. Okay, so if we want to solve this for alpha, we divide both sides by n, and we say alpha is equal to theta plus 2 pi times k all over n. So now we have our two components. So if we look back up here, we say we have our complex number z, which is equal to our radius r times cosine theta plus I sine of theta. Then the n distinct complex roots are the nth root of r, look at that right there, times cosine of theta plus 2 pi k over n, look there, plus I sine of theta plus 2 pi k over n. Okay, so that was a lot that I just hurled at you right there. Take a minute. If you need to rewind, rewatch it, do that. Then we're going to go through an example. Okay, so our k values start at 0 and then go up through n minus 1, where n is the root that you're trying to find. So we're going to go through and we're going to do the example of 1. Okay, I'm just going to write it down here so I have more room. So my complex number z is equal to 1, which we can write as 1 times the cosine of 0 plus I times the sine of 0. Okay, because cosine of 0 is 1, sine of 0 is 0, distribute that 1 in, yada, yada, yada. So r is equal to 1 and theta is equal to 0. Or 2 pi, if you want to use that, that's fine too. So if we want to find the cube roots, then n equals 3. So first we start with our k, where k is equal to 0. We plug that into this crazy long formula right here. So doing that, we take the cube root of 1 times the cosine of theta, which is 0, plus 2 pi times k, which in this case we're doing k equals 0, all divided by n, which is 3, plus I times sine of that same whole shebang. So 0 plus 2 pi times 0 all over 3. Simplifying this down, cube root of 1, 1. And then we have cosine of 0 plus 0, because 2 pi times 0 is 0, over 3. So cosine of 0 plus I sine of 0. This is 1, this is 0. This gives us 1. That's our first cube root. Now we move on to where k is equal to 1. So when k equals 1, we do the same shebang that we just did. So plugging it into this same formula, we take the nth root, so the cube root of 1, times the cosine of, our theta hasn't changed, it's still 0, plus 2 pi times 1 all over 3, plus I times sine of 0 plus 2 pi times 1 all over 3. Now we can simplify this down. Cube root of 1, still 1. Now 0 plus 2 pi times 1, it's just 2 pi, so we have the cosine of 2 pi over 3 plus I times sine of 2 pi over 3. Now, this is where the unit circle comes in. We know that we can just distribute this 1, we don't have to keep writing it. The cosine of 2 pi over 3 is negative 1/2, and then the sine of 2 pi over 3 is square root of 3 over 2 times I. Look at that. That's one of those that I mentioned right up here. Moving on to our last one, where k is equal to 2, because we go up to n minus 1, so 3 minus 2, or 3 minus 1 is 2, okay? So k is equal to 2. We plug into that same whole formula, cube root of 1 times cosine 0 plus 2 pi times 2 over 3 plus I sine of 0 plus 2 pi times 2 over 3. Cube root of 1 equals 1. Cosine of, this will be 4 pi over 3 plus I sine of 4 pi over 3. Okay, we don't have to keep writing this 1. We know that the cosine of 4 pi over 3 is equal to negative 1/2, and then the sine of 4 pi over 3 is the square root of 3 over 2 times I. And that is the third one that I mentioned right up here. Okay, so I'm going to go through and do a couple more videos of examples. If you feel like you got this, go ahead and start the homework. If you are totally lost, don't feel bad because this is super confusing. Click on the next video and I'll help you out some more.